So let's move on then to 1D transient problems. Great segue. What we're going to be doing now is maybe sort of obvious, but we're taking the stuff that we've done with numerical transient problems, the lump capacitance transient problems we already talked about, and we're introducing a dimension in space. So we've done stuff separately for looking at spatial numerical models, for temporal numerical models. We're just combining them. And it literally is just a combination. It's really kind of straightforward how it works, but it's good to walk through the procedure to see it and get comfortable with it so that you can actually implement those. So just a reminder of the methodology here. We have this set of general steps. First, we're going to distribute nodes spatially throughout the computational domain. That would be, let's say this is a 1D problem, so let's call that X. So we're setting up a mesh of X positions at which we're going to place nodes and do evaluation. We carry out an energy balance on each node, and then that's going to lead us to a state equation. So this is how it's the combination of both the spatial and temporal. So we have state equations coming out of this procedure, as opposed to just like a pure energy balance that you get for like a spatial only problem. So then we have our state equations. We just integrate forward in time by stepping either with Euler's or Heinz or RK4 or whatever it might be. So that's kind of the procedure. We'll just go through an example for this. So our example is we're going to take a fin. The fin is initially at equilibrium with surroundings at t infinity, at time equals 0, and we are forcing a heat transfer to occur at the base of this fin at the rate of 0.5 watts, and then you have this, this kind of geometry. So I guess it's probably a cylindrical fin, given that it's a diameter. And then the tip is adiabatic. Okay, so let's walk through this example. The first thing we're going to do, like we said, is discretize the domain for space. So I've already gone through and placed a node here at 1, 2, at I, at n. Or you might also draw the positions of I plus 1, I minus 1. You might have n minus 1 here. So this is, the important points are all the delta x's are consistent, right? We aren't changing delta x based on n condition or anything like that. So we just set that up, and then we describe the positions as x sub I is equal to I minus 1 over n minus 1 for I equals 1 to n. If you're doing this in Python, it would be just I over n minus 1, since it's zero-based indexing. Okay, and then our delta x is equal to L over n minus 1. So then you might sort of anticipate that there's going to be more here that relates to time. Let's just start with this spatial problem, and then we'll add in the time bookkeeping later. So step 2, let's carry out an energy balance on each node. Let's look first at the node I. So we're going to have, again, trying to draw everything going in, just for consistency, something from the left hand by conduction, something from the right hand by conduction, convection from the surroundings, and then we have this new part, right, the du dt. So that's new for this type of problem. So writing out the energy balance there, I guess we would have q dot LHS plus q dot RHS plus q dot convection is equal to du dt. So we have everything in, and then remember out and stored are on the other side. So stored is going to be here. So we need terms for each of these. The terms for the conduction are Fourier's law. So it would be, let's say, I'll just write it out equivalently here. So first we would have conductivity times cross-sectional area over delta x times t at I minus 1 minus ti. Right? And this has come up, by the way, a few times. So sorry if I'm repeating myself, but why is there no minus sign here? Right? Isn't Fourier's law minus k ac dt dx? So why is there no minus sign there? So the answer is delta x here is assumed to be positive. Right? In Fourier's law, it's a negative step because you're saying you're going from the source temperature, which is going to have a smaller x position than the sink temperature. So then that x becomes negative in Fourier's law. So if it's a numerical approximation where we're assuming delta x is positive, then this term, the whole thing becomes positive. Just to clarify that. So that's the left-hand side. The right-hand side is what? It's same thing, k AC over delta x, Ti plus 1 minus Ti. And then convection is going to be h bar perimeter times the area, which is, well, delta x times perimeter is our area. Times T infinity minus Ti. And then all that's equal to, on the right-hand side, rho C AC delta x times dt I dt. Again, this is mass, rho times AC delta x. That's the mass of that volume. Delta x is the width. And then specific heat, and then our gradient. So we are trying to solve this equation for this derivative. That's our state equation. All we need to do is algebraically just solve this entire thing for dt dt. So let's see. This is, by the way, for I is equal to 2 up to n minus 1. So that's the internal node. We can do something similar for the other nodes. We'll just go through that quickly. So this, the first node is basically the same method, except we have a specified Q coming in from the left-hand side. We have du dt, but we'll note that the control volume is just half, right? Same as same as the other problems where we're just dealing with half of the volume here, but that affects the du dt term as well. So we can write this out. It is the top would be q dot. So q dot was specified, right? Q dot plus q dot right-hand side plus q dot convection is equal to du dt. And then writing this out, it would be q dot plus k AC over delta x T2 minus T1 plus h bar perimeter times delta x over 2. Again, that's our area for convection. That's delta x over 2 times the perimeter times T infinity minus T1 is equal to rho C AC delta x over 2 dt 1 dt. It's all the same except for the delta x is over 2 and then our specified heat flux. On the bottom node, it's again the same. The only difference is going to be we aren't forcing a q dot in from the right-hand side, so that's just 0 there. So I'll just write out the final answer there just so you have it. It is what? Let's write it this way. So k AC over delta x Tn minus 1 minus Tn plus h bar perimeter delta x over 2 T infinity minus Tn is equal to rho C AC delta x over 2 times dt n dx. Thank you. D time. Okay. So like I said, our objective in all this is now solve for these dt dt's. That's all we need to do, and then we can implement whatever method we want. So for this, just to have one of them, right, we'd be saying dt n dt is equal to, I guess, 2 alpha over delta x squared. So remember, alpha is k over rho c. So we're just simplifying that times t n minus 1 minus t n plus h bar perimeter over ac rho c times t infinity minus t n. So this, do the same thing for the others. We now have a vector of dt dt's. Right? We always want to come out of this with a vector of dt dt's that we can then use to step forward in time. Questions on this? Yeah.
What are those constants again? Alpha and alpha?
Which?
Oh, that.
Alpha is k over rho c, the thermal diffusivity.
2 times alpha?
Oh, sorry. I'm sorry, yeah. 2 times alpha. It's basically the same thing. I've discovered I'm really inconsistent with my 2's, by the way. Sometimes I do it like this, and sometimes I don't know. I can't explain it. It's like if I give extra thought to a 2, then it becomes loopy. I don't know. Sorry about that. Any other questions on this? Okay. So we now have a vector of dt dt's for space, right? For every single spatial node, you have a dt dt. Then we need to figure out how to step forward in time. So again, we go through and we'll discretize our domain in time, and we'd say my time step tj is equal to j minus 1 over m minus 1 times t sim for j equals 1 to m. So I now have a discrete time for every value for every single time. And then I'm just going to use that to move forward. What else do I need? So let's note that delta t is equal to t sim over m minus 1. And then we need to kind of go back to our temperature to add in this bookkeeping for time. So this is really the trick, I'd say, aside from sign issues and or energy balance issues, like the bookkeeping is the tricky part. So we need to go back and modify our temperature vector. And let's say we're going to use, let's use I for space. We're going to use J for time. So we would say T, I, comma, J for everything. So T, space, and time. Now, it doesn't matter which order you do it in, just do it consistently. And the other thing is, if you're doing this in Python or MATLAB or whatever, and you go to plot, a bunch of temperatures, you might prefer to have one of the indices in one position or the other. So again, it doesn't really matter. It just ends up giving you kind of a different shape of your matrix when it comes time to do something with it. So, okay, let's also note the following, that our initial condition is going to be temperature for every node I at time step 1 is equal to T infinity for I equals 1 to n. So it's kind of like the spatial 2D problems where you have, you're keeping track of one index at a time. Here we would say, I'm going to vary the index I from 1 to n. And for every index I, I'm going to say T I, the first entry in that vector, is going to equal T infinity. So you can imagine this kind of 2D matrix, and you're going through and you're filling out the first value of every row here. And then as you go forward in columns, you're going to be adding the temperatures as a function of time in each column. Okay, so let's keep going on this. Let's say we go through and we solve all of our energy balance equations to get state equations. The first thing we would do then is probably try to employ our simplest technique, which is Euler's to step forward in time. And the way we're going to do that is we'll say, I'm going to look at T, my temperature, at some position I, like that's our first index, and then in the second index, that would be my next time. So I'm going at the position I at the next time, j plus 1, is going to have to be calculated based on the current temperature at that time, at that position, plus the rate of change with respect to time for that position times delta t. All right, so just like stare at the indices and make sure they make sense to you, because that's really the complexity here. So Euler's technique is pretty similar. I guess what we could do is write out, what is that going to help? Let's actually just look at how the program's implemented. One tip that I'll give you though in doing this is it kind of becomes mentally draining to keep track of I plus 1s, I minus 1s, and all that, j plus 1s. So the way that you can do this to kind of make it easier, more intuitive for yourself, is to do everything for the first step, the first time step. So you keep track of all the i's as part of that, and that's fine. But just say, okay, let's go ti2 is equal to ti1 plus dt1 dt, and do it everything for the first step. And then after you're confident that you can step forward 1, then go back and just substitute out the 2's for j plus 1s and the 1's for j's. And then it kind of keeps it easy on you.